I'll be talking about using ASP.NET asynchronous programming today. Before I proceed further, I want to just check how many of you have really used async programming in developing web applications. Okay, that's it? How many of you know what is async programming? A few more. Okay, so I think I've got the right set of audience, a mix and match of people who know ASP.NET Async and people who don't know async. So I hope this talk of mine helps you understanding what is new in ASP.NET asynchronous programming in terms of ASP.NET 4.5. So before we delve into that, I want to just present a tale of two developers. So we have a developer 1 who has actually written a website and is currently in the phase of stress testing. So he is very excited about the website and he is telling his fellow friend, hey, I just wrote my website and it is going in a stress testing phase. The other developer asks him, well, that's great. Have you actually implemented asynchronous programming pattern? Because that makes your stress testing phases go very smoothly. And to which our first developer replies by saying, async, what exactly is async? Never heard about it. I have made a standard website and I don't think I need any of the async functionality in my standard website. Quote unquote standard website. If at the end of this session I'm able to change your notion that a standard website does not require ASP.NET asynchronous programming, I believe I would have achieved something. Because there is nothing like any web application that I can think about in today's world which you should write without using async programming pattern in ASP.NET. So let's quickly understand what exactly is async programming. It's about yielding results while waiting on an operation which is long running. In other words, you are basically ensuring that you are able to do work on a thread which is waiting on something else, probably a back-end operation. You are able to use that thread for doing something else. That in simple words is what is async programming in general. It lets you achieve a good performance because you are now efficiently making use of your resources. It lets you achieve parallelism because while you are waiting on something else, you are able to consume your resources to make a call to something else. So you are able to do two parallel operations at a given point of time. It also helps you improve your throughput or scalability because now that you have consumed lesser resources on your machine or in your process, you are able to serve more requests at a given point of time. So all in all, it serves a variety of solutions, or it presents a variety of solutions to a lot of problems that people deal with while writing performant web applications. Let's now understand some of the scenarios where asynchronous programming really makes sense. Typically, we have seen a lot of the programming applications that you are writing today fall into that first bucket, which is I/O bound. You, at this point of time, are writing a web application which is network I/O bound. And by network I/O bound, I mean you are making a web service call. You're using HTTP web request to make a remote web request call. You're probably using sockets to go outside of the machine and get some data. And all these are operations of a network bound I/O. If in your application you're doing any one of these three things, then you should really use asynchronous programming pattern. The other major thing, let's look at. Every web application today goes to the database to get some data. Even a database is an I/O bound operation because you are actually waiting on the database to return you results while your program is running. Even that's an I/O bound operation. Let's talk about another thing which is more frequently used in today's applications, and that's about file system. Even file system is an I/O bound operation. You are actually going into the file I/O kernel, waiting on an event notification to be triggered while you are reading a file, and that's why that also becomes another I/O bound operation. And if you look at this category, I can't think of an application which is developed today which is not using any of these scenarios. So it makes a perfect candidate for you to use async programming in today's world if you are using any of these scenarios, which I believe you are. The other real world scenario or the real time scenario that I can think about is with async programming you achieve parallelism. Let's say I have written a web application which has a page load which gets to a database, makes a web service call, reads something else from somewhere else. I'm running all three operations in my page load synchronously, one after the other, which means if any of these, let's say the third operation takes longer time to run, or I would say the first operation takes longer time to run, my third operation has to wait unnecessarily because my first operation is taking a long time. So you can achieve parallelism by using asynchronous programming, and it lets you do more than one task at a given point of time. The third scenario where asynchronous programming pattern makes a lot of sense is an event-driven web application. What is really an event-driven web application? Let's say you're using polling. A lot of you have used AJAX. You will make a call to the server. You will keep on polling in a loop. Hey, has the data come? Has the data come? Has the data come? You keep on doing that. So that's like a polling scenario, whereas all you need to know is the server to tell you when the data has come, so that you don't have to poll that many requests to the server. So that's about event-driven, wherein there is a guy or there's a piece of program which raises an event and there is a listener for that event. If you need something like that, async programming makes a lot of sense. A real classic example of event-driven programming in web applications is WebSockets, which exists today in ASP.NET 4.5, and SignalR, which is actually a higher level abstraction on top of WebSockets. Of course, streaming is another example wherein you are downloading a lot of data from, let's say, media data or a high file data from a remote location. Even in that scenario, asynchronous programming makes a lot of sense to use. So with that, let's see how async programming has evolved in these years. Funny enough, async has always been there since ASP.NET 1.1. It wasn't in 1.0, by the way. So since 1.1, async programming has always been there, but even today, I don't see too many people really using it. I can actually find an answer for that question. I believe it wasn't very easy for you to use an asynchronous programming pattern. You had to refactor a lot of your code if you have to going from a sync to an async based version, and that's primarily the reason why I believe this beautiful pattern was not adopted that much as it should have been adopted. So let's see how the code used to look like if you're in ASP.NET 1.1. You had to use what we call as async result. You'll have a begin operation, and you will not make a blocking call at your begin operation. Immediately after the begin operation, the control yields to the next line, in which case, if you are in ASP.NET 1.1, you have to check for async result.isCompleted method to see whether the task that you initiated got finished or not. So even though asynchronous programming was there, you had to kind of make this check in your program to see whether the task which I initiated at a given point of time, whether that finished or not. And people who had really implemented this would know the pains of it. You have to be very careful with using async results. You have to preserve the state that you have to pass to the next method. You have to be very careful on which thread you come back once the begin operation finished. So there were a lot of things to keep in mind. There were a lot of problems associated with this pattern, and it actually didn't become that famous, but it was there. While you made the begin operation call, you could do some independent stuff after the call to make sure you're running multiple operations at a given point of time. So that's about 1.1. 2.0 introduced what we call as an event-driven model. So if you have written a web service call which was async, this is how the code for that would look like. You had a async method when you add a web reference to a web service. You always had an async method, and you had a completed event handler. So you will call the async method and you will hook on to the completed event handler. Your completed event handler will get called once that operation finishes. So in other words, what would happen in this situation is, once I made the hello world async call, my code will not block on this line, even if my web service call is happening. So my code continues execution on the next line of code, which can be any parallel work. And once my web service call finishes, my hello world completed handler will be called, and I can retrieve the results of my web service call in e.result. So that's how the 2.0 programming pattern was a slightly better than 1.1. It still required a little bit of refactoring of the code, but the IDE and the runtime tools made it really easy for you to subscribe to these events and take actions when the events are completed. 4.0 introduced the revolutionary task panel library, which kind of brought too many things into picture. So you can now have a type called task of T. In the T, you can have a particular type which will be returned on a result of a async method call. You can do you can say hello world async on a object, and then you don't have to listen, or you don't have an end method in this case. You just say hello world async, and the results of this method call are encapsulated in a task for you. So if you see there, what you have on the slide, we have a task representing a type of hello world response, and we are calling hello world async. Hello world async in essence is returning us a task to the method, and the task encapsulates the result. So I don't need to write an end method to it. I can just check t.result, and if I want to check whether t completed or not, I can check t.status. So slightly lesser code, but still not there is what I would call. And 4.5 introduced these async and awaits, which really changed the game, as I believe. So in 4.5, what you have is, you have the hello world async method as you had in 4.0, but now you need not check the t.status. That is done automatically for you. So you just make the hello world async call, and you have this beautiful await keyword, which acts as a callback for your method. So the way this code is executed is, client.helloworldasync is executed, and the moment the runtime detects a await keyword, the rest of the function becomes a callback, and when your hello world async method finishes, the compiler or the runtime takes care of bringing back the synchronization context for you and let you resume the function after the await keyword. So let's just understand it a little bit more by looking at this function. In this function, what I'm doing is I'm actually making a web service call in an asynchronous way as in ASP.NET 4.5. So I have the new class HTTP client, which was introduced in 4.0 or 4.5, I forgot where it was introduced, but this replaces the system.net.web client class with better functionality now in 4.5. So what I'm doing is I'm creating an object of HTTP client, nothing great there, and I call the client.getString async method. Okay? Now notice here that even though I'm doing client.getString async, my code is not stopping there. The actual async call to this web service is happening on another thread in the background, and I am able to do any independent work after this service call. So in other words, I made a web service call which probably went on a different thread. I am back in my function doing some independent work, and the moment the runtime encounters the await keyword, which is over here, that's when the program will realize, hey, at this particular stage, I need to wait till the time the operation finishes. So the difference here is I am not waiting, I am awaiting. I'm asynchronously waiting in this situation, which means I will get at this, the moment I get at this point, my execution from this point onwards will only continue once my web service call has finished. That's something to consider and think about. The runtime automatically takes care of ensuring that the code after the await keyword gets executed once my async method finishes, and that makes it very easy for you to write code which looks like synchronous code but is actually performing in an asynchronous method. So just look at it once more time. The moment I encounter the await line, the control returns back to the caller, okay, in which case the runtime takes care of ensuring that once my async task has completed, the rest of the method after the await, which has now been made a callback for the async method, gets executed after the async method finishes. So me as a programmer, all I have to do is make sure that my code is calling method asynchronously and awaiting on that method call at the right point of time. So to be able to use async and await, there are a couple of things that need to be done. First, every async method should return a task or task of type T. So you can return a task in case you don't want to return anything, or return anything as a result of your method, or you return a task of any type that you want to return. In this case, I'm returning an int. I can return any type for that matter. And the method needs to be prepended by the async keyword. That is what tells the runtime that, hey, you know what, I may encounter a await keyword in this method, so that means I have to handle this particular method a little differently than the other methods. And of course, you can only use async, you can only use await if you have marked your method as async. Or you can use both of them need to be there to be able to achieve async programming. If you just put one and not the other, you are really not achieving anything. So that's about async and await in ASP.NET 4, in .NET 4.5. That's a lot of talking. I'll show a quick demo which probably simplifies this to some extent. So I'll switch to my machine. I'll just, okay. So I have Visual Studio here, and I'll hide the Solution Explorer. So this is how my page load is looking like for now. Simple web application is having a page load which basically makes a call to an external service calling, yeah. 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 So the service call will actually happen on this particular stage. I'll make the service call once I make get string async. Immediately after that, my service call is happening on a separate thread. Yeah, do independent work. That is similar. That is basically trying to say that while your web service call is happening, you can do some independent work which is irrelevant of that web service call. Brilliant question. What happens if I am doing independent work and my web service call finishes? Actually nothing. You will continue running your independent work. We will wait for the web service call only when we encounter await. So in the do independent work, I can do 10 things. As long as I don't have the await on the task that I started as a result of get string async, I will not wait on the web service call. I can continue running that code in synchronous manner, and I will come to this portion only if I am doing an await. So the question is, in this case, is it acting as a completed event? Well, I would put it in a slightly different way. Await is like a promise to the compiler that I will return some data in this task once the task finishes. So when I make a call to my get string async method, I'm not blocking execution there. I'm just letting it run. Whenever I await on my task, that's when the data that will be returned by the task, that's where I'm halting my execution. Okay? Did I answer? Okay, great. Yeah. Uh-huh. Exactly what I'm going to show you. Yeah. I'll just show this quick demo, and I think that will answer most of the confusions that you might have. Let's go back to my Visual Studio. Yeah. The Visual Studio code? I'll do it. This is not visible? Is this better? Great. Okay. So I'll move around a little to show you what the code is doing. So this is the page load method. Every page has a page load method. In the page load, what I'm doing is I'm making a web API call, new in ASP.NET 4.5 MVC or MVC 5, making a web API call to get some data. And all I'm doing is I'm getting some JSON data, serializing or deserializing into a list of type. Let me show you the type. Sales item. And I basically get a list here, and I bind that particular list to a repeater, and I do a repeater.data bind. Something that we have been doing in ASP.NET for many years now. The other thing which I'm doing in this method is I'm making a SQL call. And I have a SQL connection object, and I'm making a SQL call to this particular procedure. I do a connection open, and I do command.execute reader, and I bind it to this object which is basically a ASP chart. So when I run this particular page, you'll see how the page looks like, but in essence, all I'm doing is I'm just running two tasks at this point synchronously. One is a web API call, the other is a SQL data binding operation. So as you notice, when I run this particular page, there is a slight delay which is happening. And the delay is basically, I have introduced a 2-second delay in both the operations. I've delayed my SQL call by 2 seconds. I've also delayed my web API call by 2 seconds. And once this loads, you can see that there's a chart which gets generated. And there is some data which is coming in this grid. So these are the two things which I am essentially doing. And since this was the first request, we'll just run it once to see the actual delay which is happening on the page. And I'm showing you the delay over, I had it here somewhere. Oh, there it is. Its resolution has freaked it out a little bit. So there's a 4-second delay in loading of this particular page. Okay, I'm not the best web designer, so pardon me for my images going here and there. So we can see this page is taking 4 seconds. Now this, as of now, is full synchronous code. Let's see in this situation how we can benefit from async programming. Well, if you look at this code, there is no dependency on the first portion of the code on the second, meaning both are independent operations. So why not make them async? Well, let's go about doing that. So all I need to do is, because we know that for me to make an async method, I need to decorate it with async. That's good. I make my page load as async. And instead of calling client.downloadString, I want to use the new class, which is the HTTP client. And HTTP client gives me a method which is getString async. Let's look at the signature of this method for a quick minute. So I hope you can see this is the max I can do. The getString async is returning a task of type string. So basically what this represents is that when this getAstring method call returns, the result of that task is encapsulated in this particular task's property, and it's telling me that I can await on it, which means I can run it asynchronously. So let's do that. So I made a call to client.getString async, and I'll change this to say var string data task. So instead of this being a string, I'm now getting a task from my getString async method. Okay, now what do I do? To get the actual value, I will do string data task dot result. Alright, so one more thing which I need to do is I need to await on this task. Oops. So that's all is required for me to change this synchronous method into a asynchronous method. Let's revise. We changed the download string to getString async. We got a task as a result of that method call. We got the result in that task, and we are now awaiting. At this point, I mean, even though I have written it like an async way, it's not going to behave that differently, because immediately after making my getString async call, I am doing an await. So I'm not doing any parallel operation after getString async, which will really make it a parallel or async operation. So before we do that, let's just go here and change my SQL call also to be in an async method. So changing SQL is very simple. I'll just say my command dot execute reader async, and you can see that the execute reader async method returns a task which encapsulates SQL data reader in it. So it's as simple as that. Now I will create another, I'll call it SQL reader task, create a new var SQL reader, which I can get from SQL RDR task dot result. And before I do this, I'll do await. So await on SQL reader task. So at this point, I've even made my SQL call asynchronously. So that's few changes. Let's make sure I didn't break anything. I'll build this and run it once. And I get the yellow screen of death, which is telling me you are trying to do an asynchronous operation on a page at a pipeline which I am not liking. So ASP.NET 4.5 does things for you where it has put some checks in its method where it detects if an async operation is happening in a particular pipeline of ASP.NET request processing. I'd rather kill your request at that time rather than let you do something dangerous which you will never be able to figure out later on. So at this point what it is saying is your page is probably a synchronous page, but you are trying to do asynchronous operation in that page which I am not liking, and it is clearly telling you that the way to fix it is you just mark your page as async true. So let's do that. And to be able to do that, let's go to Solution Explorer, go to my page, which is actually here, and call it async equals true. Okay, save it and run it. So at this point we changed the code to be async, and one thing if you notice is if you look at this top time shown, it's showing you 4 seconds because we are still running things one after the other. We're not running them in parallel. And running them in parallel is as simple as ensuring that I make the 2 calls to my async methods one after the other without awaiting on them. So all I need to do is take this portion of the first await code block, take it out of here, and do it after I am making a call to my SQL. So I can put it after I call execute reader async. Also, I am just trying to make sure that I am calling both the async methods at once before awaiting. And I will get rid of this await command here and move this to the bottom. Actually, I'll move this portion here. Oops. I'll take this portion here and put it here so that I don't end up causing problems to my data reader objects. And I'll change these 2 await commands into one await command by doing task.when all, and I'll pass both these tasks to it. And I of course need to await here. So what I'm doing is I made sure that, let's just look at it one more time, there was a couple of changes. I am ensuring that after my client.getString async method, I am doing some other operation which is independent of the first operation, and I am also executing the second operation asynchronously, which is right here. And now when I need the data returned from both the operations, I basically await on both the tasks that I started. Once I await on both the tasks, I am now getting the data from these tasks in my code and using it to display the page. So hopefully this will show what we want to see. So I'm running the first request. The first request will be a bit slow, so I'll just refresh the page one more time to see the actual time it took. And we can see we reduced the time of the page from 4 seconds to 2 seconds by ensuring that the operations that we carried out are done parallelly by running asynchronous code. So I hope you would now be able to see why asynchronous programming makes a lot of sense for you to use, because end of the day I work on so many applications. I help people on so many applications where they are doing things like this, where they're making one call here, another call here. Your web interfaces are becoming interesting day by day. They are becoming heavy day by day. You are getting data from X source, Y source, Z source. But you can just achieve a lot of performance gain by running these tasks in parallel and by using asynchronous way of programming. Any quick questions at this point? Anything which is not clear? Then I'll move to the next part. Yeah. Can I make concurrent calls and still use await? That's exactly what we did. We are running both these code to the same service, yes. As long as your service excuse me, as long as your service does not find it bad that the same client is calling you the second time, you can do it. Of course, it is designed for those kind of situations, I would say. Yeah. It can. So the thing is, if you await on the result immediately after the async call, you're not achieving parallelism on that. If you are awaiting on task, that gives you much more flexibility to handle exceptions as well. So I would always suggest awaiting on tasks rather than the results. Forever. So brilliant question. How to make sure that, how do I handle the situation wherein my async call just runs forever and never finishes? Well, we have something called as cancellation token source that you can pass in almost every async method. You pass it either a timeout or you pass a cancellation token source object specifying after how much time should you return me even if the call has not completed. So there will be lots and lots of timeouts in web services and web applications. I'll try to clarify your question. Will it override the server-side timeout? No, there is no way you can override the server-side timeout. The timeout that you are configuring through async call is a timeout that you are making from the client. So I am saying cancel this call even if it takes more than X number of seconds. I'm not dealing with any server-side timeout or request execution timeout for that matter. Another thing to note here is, what if I time out after, let's say, 100 seconds, but on this particular server, I have set my request execution timeout to 90 seconds. What happens is, ASP.NET is a little intelligent, or the way they have provided this functionality to you is, if we detect that an async call, if you're making an async call within your page or within your web application, we suspend the timer for execution timeout. What we do really is, we will not take into effect that 90-second timeout that is there for all web requests, because we think if you're running an async operation, you are probably expecting that to take some amount of time, and that can be longer than 90 seconds also. So for all the async outbound calls which you make from your web application, we suspend the execution timeout timer at that point, and we continue it after the async call has finished. In case you want to override that, you can pass the timeout to your async methods or derive from objects from cancellation token source, which will let you achieve this functionality. Yeah. One last question and I'll have to move forward. Hold it right there. I'll be coming to that. I can take one more, sir. Yeah. Right. I am not keeping two objects in the task. I am awaiting two tasks. So what I have done is, I have done task.whenAll. I can await on these tasks one by one. Like I'll say await SQL data task, await string data task. Then, great question. So I'll just read out the question to you. What if my second task depends on the output of the first task? That's the question, right? What if my second task's result depends on the output of the first task? When in that case, what you have is task.continueWith. That's another function which is supported out of task panel library. If you guys have never worked with task panel library, I really encourage you to use it, because it has a whole set of functionality which lets you use parallelism and asynchronous code in modern applications. So in which case you can do task.continueWith and pass both the tasks. So I can say task1.continueWith the other task, in which case my second task depends on the output of the first task. Okay, yes sir, one last question. I'm saying last too many times. Hold on to that, I'll come to it. Okay, so I have this demo made it clear as to how to use asynchronous programming in pages as of now. Let's look at the next thing now. write. So my first developer is now saying, hey, okay, so I understood what is concurrency and parallelism, but you didn't talk about throughput and you didn't talk about scalability. You said it helps in improving both of those. How does that come into picture? Let's just see. So to understand throughput, scalability, and these worker threads and everything that some people talked about while I was explaining async, we have to understand the ASP.NET request processing flow, how requests are served by IIS as a hosting platform within, how ASP.NET requests are served as a hosting platform within IIS. So you have a kernel mode component, which is http.sys, which contains queues per application pool. So in my diagram here, what I'm showing you that there are two queues, one queue for default app pool and the other queue for another app pool which exists on my machine. Whenever you make a request, an ASP.NET request to an IIS server, your request always goes to the kernel queue first. Okay? So the first thing happens is your request reaches the kernel queue and it sits there. Now we have a user mode component which is called w3wp.exe or the IIS worker process.exe, which is the sole engine for serving your web requests. Inside that exe you have threads of various kinds, and one type of threads that you have within that exe are called IIS worker threads. Don't confuse them with ASP.NET threads at this point. These are pure IIS worker threads whose job is to take the request from the kernel queue, find the right handler associated to that request, and give the request to that particular handler. That's the only job of an IIS worker thread. It doesn't execute the thread, it doesn't execute the request, it knows nothing about the request. His job is figure out, take the request, check the extension, is it HTML? Okay, give it to the kernel to serve. Is it ASP? Okay, give it to ASP.dll to serve. Is it ASPX? Give it to the managed pipeline handler to serve. So these threads are based on IO operations, used on IO completion ports, and they are very efficient in picking up the request from the kernel queue and giving it to the to the right handler which are supposed to serve these requests. So for a ASP.NET request, these thread will pick up the request from the kernel queue and give it to the managed pipeline handler. Now the managed pipeline handler, what it does is once it gets the request, it calls a native equivalent function of threadpool.queueUserWorkItem. You guys heard about that method? QUserWorkItem? A very common method which ASP.NET developers use to queue work behind worker threads or to achieve parallelism to some extent. They have always debated that theory, by the way. So anyways, the managed pipeline handler takes your request, calls the native version of threadpool.queueUserWorkItem and hands it over to the CLR Thread Pool. From that point onwards, the excuse me, the IIS worker thread is freed up, and now it's the job of the CLR Thread Pool to execute the request. Let's see what happens when the request reaches the CLR Thread Pool. So what exactly is CLR Thread Pool? CLR Thread Pool is basically a pool of threads which CLR maintains. It is dynamic, as in it starts with some number and it grows or expands as it needs to. What I mean by need to, what I really mean is it expands when it sees that there is more load to run and I do not have enough threads to run. And by threads at this point, I'm saying about worker threads, but it applies to IO threads as well, which we'll just see what is the difference. So CLR Thread Pool is dynamic in nature, meaning it expands and shrinks based on the load. It is self-tuning. By self-tuning, I mean it checks the resource utilization on your server. Okay, if we are in a high CPU situation, CLR Thread Pool will not create more threads because he feels there's already a high CPU situation. Why should I go ahead and create more threads? So it is self-tuning to some extent. It is configurable. You can always change these numbers that the thread pool uses to maintain these pool of threads and the max it can reach and stuff like that. So let's draw our attention to the major piece of equation here, which is our worker thread. As we saw in the last slide, these worker threads are the threads whose job is to execute the request. So in short, these worker threads are designed to do work. Once your request comes, you are executed on a worker thread. And what this means is, if you have your page load method, your code inside the page load method gets executed on the worker thread, which is okay, you may not care about it that much, but what you should really know is that you can have only X number of worker threads in the process. And that number is designed or decided by the setting called max worker threads, which interestingly till 4.5 was 100 multiplied by number of CPU. You may think, hey, 100 into number of CPU, that's, let's say on a 4-prong box, I have 400 threads to handle the request, that's pretty fine. I don't need to care about that much. But the deal is, if your website is getting burst load of requests, let's say you have written a web application which is maybe like something like a Facebook, some event gets triggered, and that day your website will handle maybe millions of hits, your website will just not scale. Your website will exhibit enormous performance problems because we don't create threads just based on the rate of request. Because, and the very reason why we don't do that is, if you end up creating, if you have a 1-to-1 ratio of number of threads created versus the number of requests that came in, you will just kill the CPU usage on the box, and the server will become practically unusable for anything else. That's the whole reason why we have 6,700 something lines of code in CLR Thread Pool to basically ensure that we do the best we can and let you achieve performance and scalability based on the request count and the CPU usage on the box. One other interesting thing to note here is, whenever you make a call to threadpool.queue user work item, you are actually using a thread from the same thread pool. It's a misconception that people see that when you use threadpool.queue user work item, you go to a background thread. You go to a background thread, but that thread is again a worker thread, which means earlier if you were able to serve 400 requests, now you can serve 399. Let's say if your 100 requests come and you have done threadpool.queue user work item 100 times, now you have consumed 200 threads from the thread pool. So keep in mind these things, that worker threads are limited in nature and they are designed to basically execute your work request. And now comes the interesting component of CLR Thread Pool, which is the IO thread, which I bet most of the people just totally forget about. This is a component of the CLR Thread Pool which is designed for asynchronous programming. This is the component which is built on top of what we call as IOCP, Input-Output Completion Ports, which is a mechanism in Windows which is designed specifically to handle input-output operations. You can essentially make 1,000 web service calls on these IO threads without getting blocked. Period. Mind it, if you want to try it, go home, make 1,000 web service calls from your web applications asynchronously and tell me how many threads you used up. You would use as little as maybe 2 or 3, because the mechanism that these guys use, the IO threads use, is built on APC, which is asynchronous procedure calls, and they are built on top of IO completion ports, which is designed in such efficient way that they are meant for IO only. So these threads are also configurable. You can increase or decrease the number of IO threads you can have within the CLR thread pool. Moving on, what happens when max worker threads limit is reached? Well, as I said, this number of threads is fixed. You cannot go beyond a certain point of time. Once this limit is reached, your requests start queuing. We have a beautiful perf counter request queued, which everybody likes to see as 0, but at times you don't see that as 0. In case you are facing intermittent delays in your web applications which are deployed in production, go and have a look at that counter, and I bet you will see that number somewhere in single digit or double digit for that matter. So once we reach this number, requests start getting queued. Also, we have a limit to how many requests you can queue. So if you exceed that limit, your website now starts throwing a 503 error. And to the user, it may behave like, hey, the website is down. The website is down. It's not serving any content. Why? Because we have hit the number of threads that I can simultaneously run at a given point of time, and I have also exhausted my request queue which existed in my process. So that's why it becomes very important for you to care about these numbers and care about these threads. The other thing to note is CLR doesn't immediately create threads for you till the time we reach max worker threads. Meaning, let's say max worker threads is 100, there are 4 processes on the box. If 400 requests come at once, I won't go and spin up 400 threads for you immediately. Why? If it happens that that server is hosting multiple web applications, it can so happen that if CLR was designed like that, one web service bad code or bad application code can end up consuming the entire CPU resources and the server will become unusable at all. So that's why the rate with which threads are injected into the process is little slow. It's almost like 500 to 1 second delay that CLR injects, CLR waits to inject a thread into the process. So keep that in mind. You can, to some extent, get rid of that delay by increasing a value called min worker threads. Min worker threads is like a soft limit that we have on the thread pool. We let you create a high number of threads till we reach min worker threads. After we have reached min worker threads, we won't let you create threads at a very fast rate. If you're in a situation wherein you really can't change the code and you need to scale it up, it would make sense for you to increase both min worker threads and max worker threads as a workaround to your problem. And as I said earlier, prior to 4.5, this max worker threads was 100 times the number of CPU. If you are running on Windows Server 2003, which I hope you are not, there's a calculation that we do which is basically reduces this number to even 12 into a number of CPU. So if you're running on Windows 2003, 4-proc box, I will only give you 48 worker threads to run your requests. So please be in mind please be aware of these settings. They are really, really important. And please be aware of what needs to be done so that we need not worry about these settings too much, and how can we write efficient code which gets around us these problems of scalability or gets around this scenarios wherein we need not worry about concurrency and scalability. So that's what I'm going to show you now. For some reason the slide didn't come, but what I had is a demo. So let me just open up this page. The last presenter was right. Whenever you come out of from PowerPoint, the extend mode gets turned on. Anyways, so I have this URL. Let me show you the code of this as well. So I have this page. Let's close some of the things which we don't need. So I have this handler, download file handler, which basically calls a web service, which is on the same machine. And this web service, I have introduced a 1.5 second delay in my web service call. And I make the request to this page a couple of times, and I can see that this page is now seeing that 1.5 second delay. And the overall time to run this page is somewhere between 1.5 seconds. So this is probably a recycle of the process happened. So I'm seeing a higher time. After I browse this page a couple of times, I should be able to see that it is taking about 1.5 seconds. So let's just stress test this page and see how the performance looks like. So I'll go here, and I'm using a tool called TinyGet, which is available in what we call as the IS6 resource kit. It allows you to send simultaneous requests without using fancy tools like stress testing and whatnot. So I'll show you what I have in this batch. Excuse me. So what I'm doing is, with TinyGet, I'm making a request to this page, and I'm making 64 requests to this page all at once. I'm passing %1 as a query string to this page just to illustrate, or just to be able to pass these requests from my IIS logs later to see how long these requests took. The only purpose of me passing a query string is so that I'm able to pass my IIS logs to see how long these requests are taking. So I'll run this page, stress, and I will say anything. I'll say full sync. And once I do that, right now TinyGet is running. It's made all these requests and it is waiting on response. So it's just showing us that it has made these many requests and it's waiting on the response. Once it finishes, we will examine our IIS logs to see how much time these requests took in total and in average. So this has finished. I'll just do an IIS reset to flush this data to the disk. And while that is going on, I'll open another command window which has log parser query, which I've written log parser queries, and I will run this command. Let's just show this command first. So I've written a log parser query that parses my logs, checks for that URI which I'm passing to my page, and basically calculates the average time taken for these requests. So I will run avg and pass it the string which I passed earlier to this command, which was full sync. And at this point I'm running a log parser query against my IIS logs and showing you the average time taken for these requests, and that comes up to 7.1 seconds. 64 requests to the same page at the given point of time made your response time go from 1.5 seconds to 7.1 seconds on average. And if you look at the individual requests, it's going to be even bad. I'll just show you all requests, which is another log parser query, and you can see that some of these pages have taken, let me just use the scroll bar, as long as 11 seconds to finish. That's what brought the average to such a high number. So let's fix that. And the way technically developers have been fixing is, hey, you know what? Max worker threads. Let's set it to 200. 200 into 4 number of processors. I'll have so many worker threads. I'll have that many worker threads. I'll never have this problem. But what you are not realizing is that when you do that, you are essentially wasting a lot of system resources by just having that many threads in your thread pool sitting idle and doing nothing. So let's look at the right way to fix this. I'll go inside my handler, and this is how my file, by the way, I never showed the code for this, so here we go. So this is how my download file handler was looking like. Very simple thing. I'm just making a service call here, WCF service call. I'm calling client.getData, and I'm displaying the result of that hello world and the time it took on the page. Pretty simple thing. Now let's see the async equivalent of this code. So the async equivalent of this code, instead of deriving from IHTTP handler, I'm deriving from HTTP task async handler. Okay, let's just zoom it a little so people can see. So instead of deriving from IHTTP handler, I'm deriving from HTTP task async handler, and that gives me a process request async method, which I can decorate with the async keyword, and I'm calling my web service call now in an asynchronous method. Okay, so that's all I did on my client. And task panel library lets you do that by just doing task, if I can type, task.delay So I've changed my sync method to an async method, so I'll just make it mark it with public async task of string, and that's all I need here. I'll also change my service contract to say task of string, save it, build it, publish it to my local IIS machine, and then just update the service reference to be on the safe side. And it's taking a few seconds. It should be done. And once I do that, I'll just rebuild this. Since I'm keeping my method name same, I don't need to change anything on my client call. In my client handler, even there I'm just doing get data. Actually, sorry, I should have told you, I'm actually making the call to the get data async method now, because the service proxy generation supports or gives me this method out of the box. That's what WCF proxy generation gives to you. So now I have updated my service, updated my project, build it and publish it, and we will run the same stress test that we did a few seconds back. Okay, so it succeeded. I'll go back to my test client. I'll just do a warm-up, which will make 2 requests to the same handler, make sure it is working. Something is not right. Oh yeah, I need to await on this. Because right now what I'm saying is delay somewhere, but don't await on it. So that's what happened. I need to just publish it one more time. And now when I run my warm-up, I should be able to see about 1.5 second delay on my subsequent requests. Okay, which I'm able to see. So my web service is still taking 1.5 seconds. Now let's run my stress test. Stress full async. So right now I'm making that many requests to the web service, and if you notice, this exe itself is telling you that we are running way too fast. And going back to my log parser window, if I say avg, I always forget the string which I pass, full async, oops. Something is not right. Sorry? No, I'm parsing based on the query string. Let's do it one more time. Stress. I think I used the same string, so I'll use a really weird string. Stress gids conf 2014 async. Hope I never used that. Let me see what I used, and I go back to here, and I'll say gids. I really made a big one now. avg gids conf 2014 async. I need to do a IIS reset so that the logs get flushed. That's looking a little promising this time. And now you can see that all the requests are averaging out at 1.5 second, which is the actual delay which is anchored in my page. So with that, I'm running out of time, so I can't. I'll just talk on this last slide and we will wrap it up. So we have introduced a lot of ASP.NET asynchrony points in 4.5. You always had the first top 3 in ASP.NET, but we introduced a lot of new ones in 4.5. You can use the async and await keywords. You can use WebSockets, which give you async programming experience. You can even read the request and responses in an async manner. And of course, I showed you the HTTP task async handler. The last thing, if you want to use ASP.NET async in 4.5, you need to have this setting in your project to be true, because this enables ASP.NET to use the right pipeline which was implemented in 4.5 for async and await tasks. So either you can change the HTTP runtime target framework version to 4.5, or you can set the use task friendly synchronization context to true in case you are not setting the target framework 4.5. So with this, last thing I want to talk about, asynchronous programming is great, but with great power comes great responsibility, as Spiderman says. So please be aware of how you are using it. You can end up deadlocking your applications or crashing your applications if you throw exceptions on IO threads or async threads, or you can even end up waiting on operations forever. So try to read about what are the best practices of using asynchronous programming in ASP.NET. Here are a few. I'm not going to cover them. So with that, I just want to thank you for your time. I hope you learned something and you will be able to implement it in your ASP.NET applications going forward. Thank you.